So a DNA-based programmable gate array, a DPGA, can be designed to implement over 100 billion distinct circuits by adding different short molecules into its tube. Segments of DNA can self-assemble into circuits that perform computations. This technology would eventually be used for diagnosing diseases within living cells. DNA computing is an emerging branch of unconventional computing which uses DNA biochemistry and molecular biology hardware instead of the traditional electronic computing. Research and development in this area concerns theory, experiments, and applications of DNA computing. Although the field originally started with the dimension or demonstrations of a computing application by Alchemist in 1994, it has now been expanded to several other avenues such as the development of storage technologies, nanoscale imaging modalities, synthetic controllers, and reaction networks, and etc. This is a fascinating area of research that could lead to many exciting developments in the future. Thanks for sharing this with me. There's interesting theories that could work with this. I'm gonna get into the article. So we have an article here from newscientist.com. Link will be in the description. So it says, mixing and matching various strands of DNA can create versatile biological computer circuits that can take the square roots of numbers or solve quadratic equations. By Carmela Pedavic Callaghan. However you say it, Callaghan. Anyway, let's get into this. A liquid computer can use strands of DNA to run over 100 billion different simple programs. It could eventually be used for diagnosing disease within living cells. Fei Wing at Shanghai Jiaotong University in China and his colleagues are set out to make circuits similar to those on a computer chip, except for it's with DNA molecules acting as wires and instructing the wires to configure in certain ways. When you enter a command on a conventional computer, it instructs electrons to flow through a specific path on a silicon chip. These circuits configurations each correspond to different mathematical operations. Adding functions to chips means adding such paths. And to replace the wiring on DNA, Wang and his team model how to combine short segments of DNA into larger structures that could serve as circuits, components, and wires or function to direct those wires to form different configurations. They put this into practice by filling tubes with DNA strands in a buffer fluid and letting them attach to each other, combining into larger molecules through chemical reactions. The researchers also equipped all the molecules with fluorescent markers so that they could keep track of what the circuit was doing based on how its parts were glowing. They called the building blocks of their computer DNA-based programmable gate arrays, DPGAs, and each DPGA could be designed to implement over 100 billion distinct circuits by adding different short molecules into its tubes. In one experiment, they connected three DPGAs comprising about 500 DNA strands to make a circuit that solves quadratic equations, and in another, they made a circuit for taking square roots. They put numbers by adding molecules of a specific shape that then participating in chemical reactions with molecules that made up the circuit, analogs to an electron moving through wires. The outputs of each circuit were molecules produced by the last reaction. The researchers could read them out by measuring their fluorescent glow. I almost said grow, oh my god. They use a similar methods to design DPGAs that could classify different small RNA molecules, picking out the ones that are known to be related to a type of renal cancer. This last experiment is the beginning of what the team ultimately wants to do with DPGA technology, because DNA molecules are inherently compatible with biological systems that could offer a natural way to do intelligent diagnostics of different kinds of diseases through direct contact with body fluids or even from within cells, says Wayne. He says that DPGA-based diagnostic devices would be highly efficient, able to run many operations at once. How old is DNA-based computing? The field of DNA-based computing started with the demonstration of a computing application by Alderman in 1994. Since then, the field has expanded into several avenues, such as the development of storage technologies, nanoscale, imaging modalities, synthetic controllers, and reaction network, etc. In 1995, the idea of DNA-based memory was proposed by Ericbaum. The field of DNA computing can be categorized as a subfield of the broader DNA nanoscience field started by Ned Seaman about a decade before Alderman demonstration. I hope this helps. Wow, it's been around since 1990. Who else has contributed to the field of DNA computing? We already know about Leonard Adleman and Ned Seaman. Let's talk about Eric Baum. He was a computer scientist who proposed the idea for DNA-based memory in 1995. Baum conjectured that a vast amount of data can be stored in a tiny amount of DNA due to its ultra-high density. That's interesting. Storing a high amounts of data like that in DNA, that's very interesting. Let's talk about John Reif. He was also a computer scientist, of course, at Duke University, who proposed two different techniques to reuse the computing DNA complexes. Reif's group first demonstrated the idea of DNA-based walker that traverse along a track similar to a line follower robot in 2003. Interesting. So what the heck was a line follower robot? So a line follower robot is an automated guided vehicle that follows a specific direction based on a particular line, usually a dark line on a light surface. The robot consists of two sensors that are installed at the front end of the robot body and two wheels that are driven by DC motors. The robot uses infrared sensors to detect the line that and control the movement of the robot with a motor driver and two motors. The robot needs to perform four sets of motion, which includes moving forward, turning left, turning right, and coming to a halt. The robot can be built using Arduino Uno and some easily accessible components. Here is a brief overview of how a line follower robot navigates. Moving forward, when both the sensors are on a white surface and the line is between the two sensors, the robot should move forward. Both the motors should rotate such that the robot moves in forward direction. Turning left, when the right sensor is on the line and the left sensor is on the white surface, the robot should turn left. The left motor should rotate while the right motor should remain stationary. So obviously turning right when the left sensor is on the line and the right sensor is on the white surface, the robot should turn right. The right motor should rotate while the left motor should remain stationary. Coming to a halt when both the sensors are on the line and the robot should come to a halt. Both the motors should stop rotating. you made it this far in the video. I appreciate you. Thank you so much. I want to know your guys' thoughts on DNA based computers, DPGAs, and how they will affect the future of technology. Like, comment, subscribe. Your boy Rose, we out. OG University and Knowledge. We in action. We back. Y'all be safe out there.